to redo this variational principle. So suppose we do have this wave function, some wave function psi, then the total energy is expectation value of the Hamiltonian operator, where you have standard bra and ket of Hamiltonian. Just in case, if wave function was provided by irresponsible colleague or irresponsible computer, we may divide this expectation value by normalization, just in case if someone forgotten to normalize wave function. Now it will be normalized for sure. So it is a thing that we are going to evaluate for true wave function and slightly different wave function. So for slightly different wave function, we may assume that I'm looking on the lowest equation, lowest line, that we have an equation psi naught, and then we artificially add as humans some small addition, and we are going to inspect how the energy of the wave function psi naught and psi of with this addition will differ from each other. And here is the illustration just to make everyone comfortable with this concept. So it's just hand drawing. It's not a big science. For example, this psi naught may be like a little hump, and this delta psi are little peaks outside of center. If you add together, it will be like a castle with two towers, right? So the variational theorem, in the extent we need it here, tells that energy of castle alone will be lower than the energy of castle with two towers. So it is a theorem that will be used in order to design algorithm, design procedure to solve for multi-electron wave function. And typically in the literature, here is the more standard way to write down this variational principle. So expectation value of Hamiltonian with bra and ket taken as ground state wave function is smaller than expectation value of Hamiltonian with bra and ket as ground state wave function plus some additional contribution. So these additional contributions are also functions distributed in the whole area of definition. So generally, we can stop here if we would have very powerful computers. There is a way to find for many electron wave function in computational way. I'm going to say some very silly idea that probably no one is trying to, but and we will not do it. So use random number generator. Throw a dice at each point of space. Assume random wave function at each point of space for each component, for each degree of freedom. So generate random wave function. Use it to compute expectation value of Hamiltonian. Repeat it again with different set of random numbers. Compare which one is getting smaller energy, is likely approaches the minimum. Then repeat again and repeat procedure at random assuming of wave function until we get minimum of energy. There is nothing wrong with it. It is just numerically inefficient. Please wave hands if you permit me to go further. Okay, thank you. So we are done with main thing for today, with variational principle, and now we need to speak a little bit more about functional form of orbitals that we will be looking for. So we need many electron wave functions, and we know how to construct many electron wave functions of one electron wave function. But you know, the atomic wave functions one electron wave functions are not changeable. They are dictated by which atoms we are using. So in some sense, if we are not looking for molecules, if you're looking only for Hartree-Fock theory for atom with many electrons, we can stop here and use a combination of atomic orbitals to build many electron wave function. The only thing left to do will be electron interaction. But since we are looking to describe molecules, we have a technical aspect. It will be not a theorem. It will be not like a major issue, major challenge for humankind. But it is a matter of convenience in describing molecules that are composed of many nuclei. We need to make a smart design of functional form of one electron wave functions, and we have partially covered it in the lab a week ago. So let me focus your attention on the first equation here. So the chi sub A is atomic orbital. A runs over all quantum numbers for given atom, for specific atom. The atomic orbitals are defined at the center of ion R capital sub I. And we are planning to construct a superposition of all atomic orbitals on each ion. Therefore, the index, summation index, runs over both A lowercase and I uppercase, where A lowercase stands for principal, orbital, magnetic, and spin quantum number for atomic orbitals, and I runs over all ions in the model. And since different molecular orbitals look differently, one needs to weight to for each specific molecular orbital one contribute atomic orbitals with different weight coefficients, expansion coefficients. By the way, I have forgotten the index I capital in front for the C coefficient. So molecular orbitals are labeled by index J, and there should be all three indices for this object C. There should be J for that index molecular orbital, A that runs over quantum numbers, and I capital that runs over different ions. Please wave hands if it sounds okay. Okay, thank you. So here's the probably last new thing that we are going to discuss today. So we are going through a chain of objects that will lead us to the answer. So the main goal, the answer that we are expecting to get is total energy. So it is a last thing on in this line. Then total energy, we are going backwards from right to the left. The last thing before we get total energy will be wave function, because as soon as we have many electron wave function, we convolute it with Hamiltonian and get total energy. And here, now let me go to the beginning of this line. So we start from position of each atom in the molecule. It is what we do when we build molecule and submit job to computation, to software. Then, so if we use computational software as a black box, we start with atomic positions and we are getting total energy as an outcome. Everything inside is just internal machinery. So this internal machinery includes chi sub a atomic orbitals, but then we will use concept of molecular orbitals that you already know how to plot, right? We covered it. And molecular orbitals are connected to atomic orbitals through expansion coefficients. So here is a little dictionary. Atomic orbital, coefficient, molecular orbital, wave function, total energy. Now, there is a question. Which of the objects in this chain are changeable and which are non-changeable? So can you please? Probably I can ask, and you may answer by waving hands. Can you change positions of atoms? Wave if you can. Okay, you are not waving, which means you cannot, because it is already input that we are not allowed to change. Can you change atomic orbitals? You are not waving, which means you agree that you cannot, and I cannot as well, because they are given by solution of hydrogen-like atoms. Now, can you change if our solution will lead to absolutely correct wave function and absolutely correct energy? Can we change them? You're not waving hands. And right now there are only two objects that we can change. So can you change molecular orbital? Wave hands if you can. Please wave hands because you can. Yes. So can you change the expansion coefficients of between atomic? Yes, 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 and molecular. Yes. Thank you for supporting this idea. So the only thing that we can change is expansion coefficients and molecular orbitals. So this is the only part that we can vary. Now so we are not deriving everything, but I want to bring you to a concept, to an idea. So on one hand, we have variational principle. On another hand, we are allowed to redefine molecular orbitals. Hi, Mary, how are you?
I'm good. Can you hear me?
Yes.
Okay, perfect. Sorry, I was really late. I was getting Chipotle.
It's sure it is a good excuse.
Okay.
Do you see the slides?
Yes, I do. Yes.
Okay. So we are going from atomic orbitals to molecular orbitals to wave functions to total energy. And the only thing that we are allowed to change are expansion coefficients that connect atomic orbitals and molecular orbitals, on one hand. On another hand, we did cover at the first 5 minutes of the lecture so-called variational principle. So we can vary something until we obtain true, absolutely correct wave function. And there will be time to define it rigorously. Now I want to just informally tell. The thing that we will vary will be expansion coefficients that connect atomic and molecular wave function. So in some sense, Hartree-Fock procedure will be a procedure to optimize shape of molecular orbitals with subsequent conversion of them through Slater determinant to wave functions to total energy until we arrive to a correct, absolutely correct structure to the best we can. So in some sense, Hartree-Fock theory is theory of optimizing shape of molecular orbitals. So in some sense, we are already done with major things. I'm going to speak through a couple of other concepts so that you'll feel more comfortable when we will go to a little bit more rigorous meeting with formulas. So we are going to set up a procedure that will make multidimensional search in the space of expansion coefficients that connect atomic and molecular orbitals. In some sense, finding lowest energy, lowest electronic energy of electronic system is analogous to finding minimum of geometry. But finding minimum of geometry, we were browsing in Cartesian space for each atomic coordinate, for each position. Now we will be browsing through in this abstract space of expansion coefficient of molecular orbitals in the basis of atomic orbitals. And this search algorithm will be declared as Hartree-Fock self-consistent procedure. So we will not rigorously define it for until next Thursday, but I just want to give you a heads up so that it's possible to deliver Hartree-Fock theory in like one slide, but then it will be not very helpful. So we better go slowly but surely. And self-consistent, I was trying to illustrate it as a snake that eats its own tail. So molecular orbitals are constructed as linear combination, as superposition of atomic orbitals with some coefficients. There are no theorems that molecular orbitals represent something real, but they're very helpful too. For example, by looking on molecular orbitals, you can tell whether your system has between given atoms, is there like a chemical bond based on the shape of the orbital. There is a little notation that equations that we will be solving will be very similar to Schrödinger equation with Schrödinger operator, but because it is Hartree-Fock theory, the H will be replaced with F. So we will be dealing with Fock operator. So please prepare. I'm going to jump back about 30 slides. Just do not feel dizzy. I will go back to very beginning and then return here. So here is the last slide we saw on the last lecture. And things that are enclosed in the curly brackets are Fock. It is a Fock operator. So it is analog to Schrödinger Hamiltonian operator, but it is operator that acts only on one electron wave function, but it has some trace, some influence of other electrons onto our favorite electron. It is the difference between Schrödinger and Fock. Okay, prepare. I'm going to jump forward again. So Fock operator. So this analog of Schrödinger equation, Fock operator, will be solved several times, again and again, for different, like, you know, we will be solving for one molecular orbital, assuming that all other orbitals are known and populated by electron. So we will be solving orbital, then populating it with electrons, then solving again. Do not rush, do not panic if it sounds strange. We will go over because it is critically important procedure. But Fock operator is solved several times. Total energy is found several times. And procedure is repeated iteratively until the total energy converges. Okay, almost done, as you see. So steps towards Hartree-Fock. we will merge together concept of Slater determinant and electron-electron interaction. So it is needed. Right now I'm covering materials that will be mostly for the next meeting. So, but we cannot do it step by step. This logical units of the Hartree-Fock theory are entangled. They like a chain are connected to each other. So we already got concept of molecular orbitals, but now we need to formulate Fock orbital, and it has some uh, things that you may never assume through human intuition. If you were dealing with computational chemistry calculations before, you may have heard about the Coulomb and exchange term. Please wave hands if you have heard about them. Okay, but it is very against human intuition. And we will see it next time that it appears from Slater determinant, which we cannot forget. So when we merge Slater determinant and electron interaction, we will be able to derive Fock operator. There will be two different, very unusual terms, especially exchange term. And Fock operator will be replacement of Hamiltonian. So by doing it carefully, we will construct such operator, Fock operator, that carries signatures of electron-electron interaction. So that's the difference between Fock and Hamiltonian. And here is a heads up for next lecture. So look at this V sub EE. You see it, right? So it is just electron-electron repulsion. And ESD, it doesn't stand for South Dakota. It stands for Slater determinant. So if we practice expectation value procedure, we need to have Bryant cat of the same wave function from left and right and operator in between. And Bryant cat, when we open them, they correspond to integration over position of first electron and second electron. You see these integrals, right? Now, this bra stands for Slater determinant on the left. Cat stands for Slater determinant on the right. They are the same, except these stars. And V sub EE is in between, right? So there are, in the bra, there are two terms. In the cat, there are two terms, and operator is just one term. What's please show with your fingers how many terms will be in the result. Two by two. How many? If you open brackets. If you multiply bracket with two terms by another bracket that has two terms. I do not hear show by fingers. No. 2 multiplied by 2. 2 multiplied by 2, show by fingers? Yes. There will be 4 terms. Excellent. We have a good success. So, and you see, some of the terms will be positive, some of them will be negative. Do not worry. I'm partially covering what we will be doing when I return on next Tuesday. So if we open this brackets, if you open this electron energy, there will be term that appears from natural order of electrons and orbitals. See, in the brackets phi 1 r1, phi 2 r2 on the left, and phi 1 r1, phi 2 r2 on the right. And the sign in front is positive. Positive sign means repulsion. Good? Now let's look on another, yeah, they're the same, another term. But if we look on one side, it is again natural order, phi 1 r1, phi 2 r2, and on other side it will be opposite order because of another term, phi 1 r2, phi 2 r1. it will come with negative sign, which means stabilization, which means attraction. So although electrons are expected to repel each other due to antisymmetry, due to Pauli, due to Slater determinant, there will be a term in equations that correspond to attraction, to stabilization of chemical system. And this is the main achievement of Fock to bring this term into the theory, because without him, with only Hartree theory, there was no stabilization and most of molecules were coming up unstable and ready to explode. Okay, so positive term Coulomb, negative term exchange, when there is no intuition, but it corresponds that instantaneous jump of electron from orbital 1 to orbital 2 and orbital 2 to orbital 1. Okay, I think it is enough for today. So please ask, turn on microphones if you have questions. Or if you don't have questions, feel free to send them by emails. Okay? So
Okay.
Assume, probably my camera is not on, but assume that I cross the hands and declare completion of the meeting.
Cool.
So please wave hands if you don't have questions.
Can you hear me?
I can, but I cannot hear the class. Class already showed that there are no questions. Okay.
Okay, I'm good.
Okay, I'm disconnecting.
All right. Have a great day.
You too. Thank you.
Okay.
Bye-bye.